Dear students, in the last session I had explained the Thevenin's theorem, but in this session I will explain the Norton's theorem. It states that a complex linear bilateral network having active or passive elements with two terminals can be reduced into a simple circuit containing a current source called ISC, that means short circuit current, and a resistance called Norton's resistance connected in parallel with it. That means it states that a complex linear bilateral network having active or passive elements with two terminals can be reduced into a simple circuit containing a current source of current ISC called short circuit current and resistance RTH called Norton's resistance connected in parallel with it. To find the Norton's equivalent of a given network, step first, consider the given network. Step 2, replace the load resistance with a short circuit in a given network. Calculate the current flowing at the load terminals, that is ISC or Norton's current. Step 3, by looking back from the load terminals in the network, by replacing the voltage source by internal resistance and current source by open circuit, we can find the equivalent resistance, that is Norton's resistance. Step 4, construct the equivalent circuit by connecting the load in parallel with IN and RN. That means Norton's current and Norton resistance. Step first, consider the given network. Step 2, remove the load resistance across the given two terminals and put a short circuit across them and find the IN and ISC, IN or ISC, that means Norton's current. ISC equals IN, that equals I into R2 divided by R2 plus R3. That means ISC equals I into R2, that means voltage I into R2 divided by total resistance in this mesh is R2 plus R3. You must calculate the value of I equals to, that means the current I is flowing in this mesh, I equals E divided by effective resistance. The effective resistance is equals to the R2 parallel R3, R2 parallel R3. These two are connected in series with the R1 plus R1. Step 3, find the equivalent resistance, that means Norton's resistance, by open circuit the terminals A and B and the voltages across are replaced by the respective internal resistance they have, otherwise they are short circuited. Then current source are open circuited. Then find the looking back resistance as seen from the load resistance. That means the circuit can be extended like this. That means the terminals A and B is stretched. It look like this. The resistances R1 and R2 are connected in parallel and these two resistance are connected in series with the R3. That means this one. So Norton's resistance is equals to R1 parallel R2 plus R3. Therefore, RTH equals to R1 into R2 divided by R1 plus R2 plus R3. That's equals to Norton's resistance. Like this, we can calculate the value of Norton's resistance. Step 4. Replace the given network by a simple circuit containing a current source of current Isc, that means Norton's current, IN, and a looking back resistance, that is Thevenin's resistance or Norton's resistance, in parallel with it. The obtained circuit is called Norton's equivalent circuit. This is the Norton's equivalent circuit. Step 5. By connecting the load at the terminals, the current through our voltage across it is found. That means we must calculate the value of IL. That means the current through the load, IL equals IN into RN divided by RN plus RL. Therefore, next we must calculate the voltage across A and B. That means voltage at the terminal A and B, VAB equals IL into RL. Like this, we can calculate the current through our voltage across A and B. Using Norton's theorem, calculate the current flowing through the 12 ohm resistance. This is a problem. This is a given network. Step first, consider the given network. Step 2, remove the resistance across the given two terminals and put a short circuit across them and find the Isc or Norton's current. Therefore, Isc equals I into R2 divided by R2 plus R3. First, we must calculate the value of I. I equals to E divided by effective resistance. So, I equals E. You know the value of E, or voltage equals 36 volts, 36 divided by, we must calculate the effective resistance. The effective resistance is equals to R2 parallel R3 plus R1. Therefore, 6 into 4 divided by 6 plus 4 plus 3, because R2 parallel R3, that means 6 parallel 4. These two are connected in series with the R1, 3 ohm. Therefore, 6 into 4 divided by 6 plus 4. These two are connected in series with the R1, that means 3 ohm plus 3. Therefore, 24 divided by 10 plus 3, that means 24 plus 30, that's equals to 10, that divided by 10, that's equals to 54 divided by 10, that's equals 5.4 ohm. The effective resistance is equals to the 5.4 ohm. Therefore, I equals 36 divided by 5.4, that's equals 6.66 amp. Next, we must calculate the value of Isc. Isc equals I into R2 divided by R2 plus R3. Therefore, Is equals to, you know the Norton's current, In equals I into R2 equals to 6 ohm divided by 6 plus 4. You know the value of I equals to 6.66 amps. Therefore, 6.66 into 6, that's equals 39.6 divided by 6 plus 4 equals to 10. 39.6 divided by 10, that's equals 3.996 amps. Therefore, Is equals 3.996 amps. Isc equals IN, Norton's current equals approximately is equals to the 4 amp. Step 3, find the equivalent resistance. That means Norton's resistance. This circuit can be extended like this. That means the terminals A and B is stretched. It looks like this. The resistance R1 and R2 are connected in parallel, and these two are connected in series with the R3. Therefore, Rn equals 6 parallel 3 plus 4. It is in series. Therefore, Rn equals 6 into 3 divided by 6 plus 3 plus 4. That means 18 by 9 plus 4. That's equals 18 plus 36 divided by 9. That's equals 54 divided by 9. That's equals to 6 ohm. The Norton's resistance equals to 6 ohm. Step 4, replace the given network by a simple circuit containing a current source of current IN, that means Norton's current, and a looking back resistance, Norton's resistance, in parallel with it, and the obtained circuit is called the Norton's equivalent circuit. This is the Norton's equivalent circuit. Step 5. Finally, by connecting the load at the terminals A and B, the current through or voltage across the load, it is found. That means IL equals IN into RN divided by RN plus RL. Therefore, IN, the value of IN equals to ISC, that is equals to 4 amp into Norton's resistance is equals to 6 ohm divided by 6 plus 6 plus so 6 plus 12. This is plus 12. This is plus 6 plus 12. So that's equals 1.33 amp. You know the value of we must calculate the value of VAB. VAB equals IL into RL. You know the value of IL. So IL equals to 1.33 into 12. Load resistance is equals to 12. So that's equals 15.96 volts. Like this, we can calculate the load current IL and the voltage across the load, that means terminals A and B. So IL equals to 1.33 amps and VAB equals 15.96 volts. Thank you.